This is a cluster, 10 billion years, twice the sun. Some of them are colored red and have enormous dimensions. They're called, for this reason, red giants. When our own sun is about the same age, it will have exhausted much of its available nuclear fuel in its interior, and it also will become a red giant. Its outer layers will expand, it will become distorted, distended. It will engulf first Mercury, then Venus, and eventually our own planet, the Earth. Our oceans will boil, our atmosphere will dissipate to space, and it's interesting to ponder whether our remote descendants, if any, will be equal to the supreme challenges of such times. But fortunately, this is all several billions of years in the future. Red giants blow their outer atmospheres off into space, forming a kind of cosmic smoke ring, like this. The remainder of the star then collapses, contracting to form an extraordinary kind of object called a white dwarf. Actually, red giants and white dwarfs are part of contemporary astronomy and not something from the Brothers Grimm, as it might sound. A white dwarf is something so dense that a teaspoonful of it would weigh a ton. The initial energy of gravitational collapse heats the star so it's white, but it has no other fuel supplies to draw upon, and it gradually cools, ending up its days as a cold, black, dead ember, little bigger than the Earth.
We turn now from the death of stars to the birth of stars. But let's be clear about the arena in space we're dealing with now, the Milky Way. You see it as a band of light across the sky, but in fact, it's a vast collection of stars, a galaxy, of which our sun is a member. There are at least 100 billion stars in the galaxy. Looking even farther out, astronomers see other galaxies as big as our own, dispersed like ships in the ocean of space. Here's one very like our own. If we could look at the Milky Way from the outside, it would appear as a spiral like this one. Or, looking sideways on, that is where the sun and Earth are. There, out to one side. But in fact, we look from the inside and see the flattened disk of stars as a streak across the sky, all around us. The view is obscured, even to powerful optical telescopes, by clouds of gas and dust that lie in the disk of the Milky Way. Radio telescopes give a better impression of the distant part of the galaxy, and of how, out of clouds like these, new stars are forming. According to mythology, the stars of the Milky Way were spilt across the sky from the breast of a nursing goddess, Juno herself. Not all that milk has yet formed its stars. The great telescope at Parkes in Australia is mapping the Milky Way by radio, and the modern painting shows the regions rich in gas, which are still capable of making new stars. The existing stars don't show up on the map, only the thin hydrogen gas lying between them. This gas broadcasts its own characteristic radio waves, which pass through the dust that obscures the starlight from distant regions. Radio astronomers can work perfectly well in daylight. The 210-foot dish at Parkes turns towards the Milky Way.
Start the scan, please, Ben.
As the telescope sweeps the Milky Way, it records strong radio waves from particular regions. In this case, a section of what is called a spiral arm. Our galaxy, like many others, turns out to have spiral arms wound around the center. As mapping continues, the pen recorder gives the astronomer an impression of what the telescope is picking up, a cross-section of the Milky Way.
Declination minus 51 degrees.
The details are recorded in a form which a computer can read. The milk of the mother goddess is registered as a code of holes, punched in a tape. The computer is the map maker. It plots the radial contours of our galaxy, seen edge-on from our vantage point within one of the spiral arms. The colors bring the disk of the Milky Way to life. The regions of strong signals are those where the galaxy still has the capacity to renew itself in new stars. But before stars can be made, the gas of the Milky Way has to form denser clouds on a relatively small scale. On the other side of the world from Parkes, British radio astronomers at Jodrell Bank seized a new opportunity for detecting small gas clouds. The mysterious pulsars are ready-made beacons lying in the Milky Way, which illuminate the beginning of star formation. Manchester University's giant dish, famous for tracking spacecraft, spends more time exploring the universe. At its focus, the radio pulses are gathered. The antenna arms find waves vibrating most strongly at one particular angle. That's because of magnetism within the pulsar itself. The angle of vibration has been twisted by invisible gas clouds in space. Thus, Graham Smith uses pulsars even without knowing exactly what they are to explore our galaxy.
Our galaxy, the Milky Way, contains between the stars a very thin gas, and we believe it's out of this thin gas that stars are made. It's been very difficult to measure how much gas there is because it is so thin. But the pulsars have given us a marvelous opportunity of doing just this. The radio pulses come through the gas and they act as a sort of probe. We can measure the delay, the time it takes for a pulse to go through, and this tells us just the amount of gas there is. Furthermore, we can also measure the size of the clouds. For example, we know that some clouds are about the size of the solar system. And so here we have the gas out of which the stars are made. But there's one problem. The stars have a magnetic field in them, and we know that this magnetic field has been shrunk into the star as the gas clouds shrink into a solid body. We'd like to know how strong the field is before it starts, and again, the pulsars have given us a measurement. The shape of the pulse, detailed shape of the pulse, changes as it travels through the gas. We've been able to measure these shape changes and measure the strength of the field. Now we have then the gas and the magnetic field, and we can begin to understand this basic process of how stars are made out of the very thinnest and coldest gas that we have. Well, let's go to 2015 plus 28. I think I've got a good calibration here.
The Orion Nebula is the best-known maternity ward of stars. It's a cloud of gas and dust studded with brand-new lights. Strange radio emissions and heat rays disclose hidden objects, which are stars in the very process of formation. The force of gravity sweeps up a huge volume of gas and heats it to make a star. The newborn stars come alight and visible to the optical telescopes. They're scrutinized from the Lick Observatory, perched on Mount Hamilton, more than 4,000 feet above the fog of San Francisco Bay. At the great 120-inch telescope at Lick, preparations are made to observe one of the very young, newly formed stars. After 20 years of work, George Herbig is a leading authority on the youngest stars. Tonight he wants to analyze the light of one of them, and this strange room is the camera he will use. Light gathered by the 120-inch telescope is guided into this room at its base. The room is kept sealed and cool, and even the heat of the astronomer's body would distort the delicate optics if he lingered too long. This curved mirror focuses the starlight onto the photographic plate. But the most important device in the system is a grating which breaks up the starlight into its component colors to make a spectrum. From features of the spectrum, the astronomer will deduce what is happening in the neighborhood of the star. The night assistant steers the telescope to the approximate position of the wanted star.
Ken,
Yes, Dr. Hervey?
3 seconds east, please.
All right, 3 seconds.
And the rate, 50 seconds in declination south.
You have 50 seconds in declination south.
All is now ready, and George Herbig, master astronomer, settles to work. The fine adjustments are made by the astronomer himself. All the while, the Earth turns, and the great telescope has to follow the star slowly and precisely, like the hour hand of a clock. The astronomer must keep the starlight falling on the slit of his big camera for as long as necessary to produce the photographic spectrum he needs. Some stars are so faint that they need an exposure of several hours. Notice how the starlight jumps about. This is the twinkling of the star caused by the astronomer's worst enemy, the turbulent atmosphere of the Earth. Seeing is the term they use to describe the degree of turbulence. It is such patient work through long, cold nights that gives the astronomer his authority to explain the workings of the universe.
What fascinates me is that we are now able to observe and partially to understand the violent activity that accompanies the birth of a new star. New ideas have come out of these studies. For example, the idea that our own planetary system is not the result of some later and independent event, but actually came about as a natural consequence of the formation of the sun itself. In fact, we, as well as the Earth, are very probably made of material that was part of the surface layers of our sun. Ken, that position of Fu Orionis was for equinox 1969. What do your dials read?
The dials read 5 hours, 43 minutes, 37 seconds.
Around the young sun, the Earth and the other planets formed. From that task, nature left some unused material, the comets. This one, the most brilliant new comet of the century, was discovered by amateur astronomers in Japan. You don't need a big telescope to spot comets. In fact, small instruments are better because they cover a wider area of the sky. Comet hunting is an ideal job for amateurs. Tsutomu Seki, co-discoverer of the famous Ikeya-Seki comet of 1965, continues his search for others on every clear night. His little observatory is on the roof of his home in Kochi, a small Japanese city. This celebrated astronomer earns his living by teaching classical guitar. Man-made lights are a nuisance to astronomers, especially to Seki, living, as he does, right in the city. He has to wait until everyone else has gone to sleep. Secchi saved for 10 years to buy these binoculars. They cost him $800. And by staying up each night until 3 in the morning, Secchi has discovered 5 new comets. Comets first appear as faint little smudges, but Secchi recognizes them intuitively at first sight. The motion of a comet can be measured from night to night in sky photographs, and Secchi uses a homemade telescope for this purpose. A friend ground the mirror for him. In more superstitious times, comets were fearful omens of disasters to come. To modernize, they are the scrap of the solar system, icy dust balls that plunge in from the depths of space and swing around the sun. Their tails are blown out like smoke in a wind of high-speed particles that pours continuously from the sun. Every astronomer has his chosen way of keeping warm on a cold night at the telescope. Secchi favors electric slippers. "20 years' experience of finding his way around the sky makes the work easier. He's able to discount the hundreds of other nebulous objects that may be mistaken for comets. As he has no electronic computer, Secchi spends 48 hours working out an orbit. Just as he taught himself to find comets and play the guitar, so he mastered the mathematics that he needs. 3 or 4 nights' observations of a comet's movements give enough information to calculate its orbit as it sweeps around the sun and heads off again into deep space. The astronomer reduces the workings of the heavens to numbers, as men have always done since they first made calendars and tracked the wanderings of the planets. But his heart, as well as his scientific curiosity, is stirred by the wonders of the night sky.
When I survey the bright celestial sphere, so rich with jewels hung that night doth like an Ethiop bride appear, my soul her wings doth spread and heavenward flies, the Almighty's mysteries to read in the large columns of the skies. For the bright firmament shoots forth no flame, so silent but is eloquent in speaking the Creator's name. No unregarded star contracts its light into so small a character removed far from our human sight. But if we steadfast look, we shall discern in it, as in some holy book, how man may heavenly knowledge learn. It tells the conqueror that far-stretched power, which his proud dangers traffic for, is but the triumph of an hour. Thus those celestial fires, though seeming mute, the fallacy of our desires, and all the pride of life confute. For they have watched since first the world had birth, and found sin in itself accursed, and nothing permanent on earth.
Nothing permanent on Earth. There's nothing permanent in the whole universe. We've seen the magnetic upheavals on the sun. We've talked about the nuclear fuel of stars and how eventually it's exhausted. We've seen gravity at work, making new stars. All of these processes far surpass the strongest efforts of natural forces on Earth. But now we must move on to events of much greater violence yet. A star is a large nuclear reactor. But some stars turn into huge nuclear bombs. and come to a far more dramatic end than is forecast for our sun in the supernova, which is the astronomer's term for an exploding star. The stars most likely to explode are massive stars, much heavier than the sun, which are very hot. They give off very strong ultraviolet rays, like the ones in the constellation of Orion. Here's another photo of the Orion Nebula, which is in Orion's sword, and which we saw earlier as a breeding ground for stars. It's been taken by invisible ultraviolet light, specially for this program by the Royal Greenwich Observatory. You see young stars burning very hot. But most of this ultraviolet light is cut off by the Earth's atmosphere, which is just as well for us, or we'd be barbecued by ultraviolet rays from the sun. It means, though, that astronomers have to use rockets and satellites to get their telescopes above the atmosphere for a good look at the hottest stars. For 10 years, American astronomers and space engineers worked on a satellite for ultraviolet astronomy. As the most complicated scientific satellite ever built, it cost $75 million, and it finally rose from Cape Kennedy just 4 months ago. The Orbiting Astronomical Observatory, or OAO, carries a battery of 11 telescopes high above the Earth. It's controlled by astronomers on the ground.
You're not big. Can you load from MagTape? Roger, Terry, we see you.
Roger.
Roger, voice, Southcom, we don't see you.
Santiago, OAO. I'm issuing a command to put you in a no verify mode. Roger. At this time, I'm going to ask you to send back experimental data.
The OAO picks up the ultraviolet light from hot stars, which the atmosphere cuts off from ground telescopes. Opening this new window on the universe demands the complex drills of space flight. Astronomers at the Goddard Space Flight Center peer, in effect, through telescopes high above the atmosphere as the OAO passes over the eastern United States.
How'd the picture look on that one, Otis? Very good.
Well, there's camera 1 reading out. We're looking at the sword in Orion right now. The central star is Theta. It's a double star. One star is 5.16 magnitude 06. The other is 5.07095. This is camera 3 right now. It's reversed from camera 1. The star field's down in the lower right-hand corner. It has a different filter on it. Getting ready to read out camera 4 right now. One of the other stars in the field is Iota. It's the one at the very bottom of the field, and it happens to be a 2.77 magnitude 09 star. And that's the end of the readout for our 3 cameras for this pass.
At the Smithsonian Astrophysical Observatory, Fred Whipple and Robert Davis take a census of ultraviolet stars. Their computers catalog 700 a day. This is Fred Whipple.
The beauty of the OAO experiment is that it registers the light in the very far ultraviolet, where the huge massive stars, very hot stars, are tremendously bright. And because these stars are very young and have very short lives compared to the sun, because even though they are more massive than the sun, they burn up their fuel at a tremendous rate and therefore have very short lives. Now, with regard to these very hot stars with their short lives, they usually end in a supernova explosion which spews out the material into space. And while this process is going on, they make out of hydrogen and helium the heavy elements, like earthy elements, that indeed constitute planets where they are formed in the system. And if it were not for these supernovae, there probably wouldn't be an Earth at all, because in the early stages, this material from such explosions collected into the solar system and produced the material that we're actually standing on here. The OAO, then, is going to be able to study these stellar nurseries in space so that we can find out just how these processes of evolution go on.
Fred Hoyle blows up stars by computer. This cosmic anarchist is the most controversial of theorists.
If you think there's a mystery about why stars explode, then you've got it all wrong. The real mystery is why stars aren't exploding all over the sky. The thing to remember about stars is that they're a battleground between gravitation and nuclear physics. Gravity is trying to pull the stars always tighter together, and nuclear physics is trying to heat up the gas and make it expand apart. When one of these battles is going on, as it is inside the sun now, the nuclear physics always holds its own. But after a time, all nuclear fuels become exhausted. And when they become exhausted, gravity wins. But the point I want to make clear to you, there isn't just one nuclear fuel, there are several. So there is a whole sequence of battles. Whilst the battle is on, nuclear physics is okay. But once the battle is over, gravity takes charge again. So the battles, as they go on, one nuclear fuel after another become more and more extreme. And in the final battles, there is the possibility that the nuclear forces, the nuclear processes, become so violent that they're able to shatter at least a portion of the star. And that is what we see in exploding stars, or supernovae, as they're called.
The wispy debris of a star that exploded thousands of years ago still glows brightly as it expands as a huge shell of gas. The Crab Nebula is the best known of the supernova remnants. It's the remains of a star that Chinese astronomers saw exploding in AD 1054, 915 years ago. Today, the Crab is a mine of information for astronomers. It's mapped by radio astronomers as one of the strongest radio sources in the sky. And rocket telescopes have detected intense X-rays coming from the cloud. One of the puzzles of the Crab Nebula has been to explain how it stays so bright 900 years after the explosion. Although it's one of the most carefully studied objects in the sky, there's one feature everyone missed until just a few months ago. What that dramatic novelty is, we'll come to later on. But here is a star brewing up right now. It's photographed for the first time in color, especially for this program, by the Mount Stromlo Observatory in Australia. This star was seen to flare up in 1843, but now it's warming up again. It's one of the strongest sources of heat rays in the sky. Eta Carini is a puzzle, really. It is less violent than a supernova, releasing an immense amount of energy, but it's doing so in slow motion. Eta Carini is 6,000 light years away. If a nearby star were to explode, it could be very unpleasant indeed. Atomic radiation from the star might force us to shelter underground. It could be like the fallout from a nuclear war, with incalculable effects on life on this planet. In fact, as nearby stars must have exploded from time to time in the history of the Earth, some astronomers think that some of the big changes in life in the past may have been due to atomic radiation from them. As it is, exploded stars far away continue to bombard the Earth with mild radiation, and it's easy to get a hint of that. This is a simple detector of atomic radiation. This radioactive material in the luminous dial of this wristwatch makes it chatter. Take it away, and we still have the odd count. Some of it may be coming from slight radioactivity in this studio, but much of it is due to cosmic rays, high-energy atomic particles coming from the depths of outer space. The latest and best evidence that they come from exploded stars is provided by Peter Fowler of Bristol University in England. He flies big balloons to pick up cosmic rays at the edge of the atmosphere before they're degraded by collision with the air. The balloons carry stacks of high-grade photographic film that records tracks of particles. The cosmic rays include representatives of all the chemical elements. But the most interesting thing is that Fowler finds very heavy elements that don't occur on Earth. The heaviest natural element is uranium, number 92, for the perfectly good reason that very heavy elements break down rather quickly into lighter elements. Here's the track made in the emulsion by the most massive particles so far encountered in the cosmic rays. It corresponds to element number 108, or thereabouts. It must have been made rather recently, and the most likely source is an exploding star, a supernova. Fred Hoyle has said, in general terms, why stars explode in a violent battle between nuclear forces and gravity. But to understand it better, we should look more closely at the life story of a star.